So by changing that, you're controlling how fast.
Over the on allo pattern, arithmetic logic unit pattern, on red alone, I'm gonna add blue, which has another logic pattern, and finally green, which is on a third channel. Now this is with only one window working. I want to try to change the speed. I can change the channels. This is just changing the red, green and blue channels, keeping the same pattern.
What we have here is something we call the Don bus, after Don MacArthur, developer of it. It consists of the start of the system starts from a clock, high frequency clock, over here at 9.7 or so megahertz, phase locked to the subcarrier. That goes to a clock generator, which generates the timing signals for the system, and also sync, clock, vertical drive, horizontal drive, etc. Goes from there to our modules, which process the digital information. Over here, the big box here is the XY generator. It's an XY data selector, and it selects these XYs, which we'll talk about in a few seconds. We have over here something called an ALU unit, arithmetic logic unit, which generates patterns and such. We have over here, on this side here, this box here, called a memory, a screen memory, and all these units are connected together by these cables, these multicolored ribbon cables, and we just patch them together for now. And finally, the output of these digital signals finally are routed up to this thing called a D to A, which converts the digital signals to an analog signal. Over here is our red, green, and blue, which patch together the outputs of the system, which go to a color encoder sitting up here, over here, and this finally puts it into video. Okay. So that's the description, not a good one, but that's the description. We also have power supplies and other little nitty-ditties. We can walk over here to this blue box you see here, having this keyboard and this monitor. And this is our terminal. It's now acting as a dumb terminal. It's called a Sol computer. And it consists of an 8080 microprocessor, but we now use it as a terminal. We can start up the system, which maybe I'll describe now. At the monitor here. I can turn it like that, if it makes it easier. 73000G. DX, take a couple of seconds here. As we sit around and wait, hear the clicking of the machines. Okay, now we get RT11, that's our operating system. And now we're going to start up something. We're going to show you a test program demonstrating the X and Y data selector, and also the X and Y, XY signals. Okay, so first we're going to try starting up the program. Let's hope it runs. Something called bar, program made by Walter Wright, and it's to demonstrate these XYs. And surprisingly, what's the story here? We end up with blue. That's not the way it's supposed to start. We know that. Okay.
This is a very nice pan. First time it worked out directly from here, from this to that.
Okay. Now it's going to take a little. We have to start this up again. So
What is this
all of you have a little
technology? It
patience.
doesn't work on the first time, or?
Oh, it just needs some setups.
I see.
So we're first going to turn all these numbers on to the right numbers. As of right now, we deal in numbers, somewhat, and somewhat in programs, sort of a hybrid system, somewhat between hardware and software. Hardware being these funny programs, and software being things the programs run, mechanics, and the software, the programs that make it run. Okay, so we should be starting up pretty soon. Now we go back to showing Walter Wright's program. We start up the system, and right now, if you look at the screen, over here, we could show bar, and it might work. Okay, and it should be demonstrating the XY, and the XY is not working. Oh, well, we'll try that again for good luck and health. 73000G. We bootstrap the system again. So you notice the DX, bootstrapping the disks, getting the system, pulling it up by its bootstraps, and letting you run the operating system called RT11, as indicated in this little left corner, RT11. Now we're going to run something called run DK1, bar. This is a program made by Walter Wright, placed together by Walter Wright, demonstrating our XY data selector and also our XY signals that are the heart of our
The guts.
Don bus, the guts. And it should be working right on your little monitor, and there it goes, right on the monitor. As you see, first time, every time, it does wonderful. And we're looking here, and it's very possible it's running, just something is not running. We'll look at it again, seeing what the...
It's called a loop, yeah. Now you got into loop.
So we're going to go through this again, just to demonstrate this program endlessly, and we'll go back and see is everything plugged together. This is also a possible mistake here. By pulling out all these wires, something might not be plugged in correctly. We'll just go through all the wires, making sure they're all patched together properly. And as I might notice, they seem patched together properly. Now we go into manual operating mode. Manual operating mode! And here we go, testing out the system. This is called testing out the system. It's one of my performances I do only occasionally here. Now we're just testing. We use in machine language, not even machine language, something called ODT, online debugging techniques. And we just run through the system and test if everything's operating. And we put a 0 here, we should see something. That's something.
Some red came on.
Red. We got some red. That's getting there. That 20 should give red. Well, it does. It gives a little. Not much. So we're missing something here. Aha. So we go back to some other magical mystery registers, which we won't mention, and set them to the proper values. Aha. That's the reason. These magical mystery registers were doing something they weren't supposed to. We set them all correctly, and we should have it back in order. Oh, that's so much better. 7-1. That's a good number. 046 sounds good to me, doesn't it? Yeah, it sounds good. Notice that all 177s, put them all to 0. Return. Oh, so much worse. Let's do it again. That's good. And now we go back to where we were before. Sometimes the programs run and the things are not patched together right. We just got to get them patched together. Okay. So I run through these different registers here. And it's getting there very fast. Woolly. 73124. Good. 171044. And we'll duplicate that 177334. And I had another magic number I could have taken out. What did I have? I changed that. Magic number, if you look on this side of the screen, you won't. Oh, my magic number is sitting next to these diskettes. Over here, notice this number, magic number 63757. This is the key number. Now, all of you who are sitting in your seats should now, or standing in your seats, should remember 63757. I'll repeat that again.
Don't tell anybody.
Okay, Murray Hill 7. We'll start that again. 171044. We're going to place in the number 63757. Got that? Okay, good. It's an important number. And now we have our test pattern on the screen that says that things are working properly. You can see in the back monitor there we have some kind of pattern of sorts.
So
Supposed to be-
unleash it, man.
Now we're
Unleash
going to start up this whole deal and see what we can get. And we should have something called Bar Bar by Walter Wright. Okay, there it goes. And now what it's indicating in the background, that red bar, is something we call our Ys. That was something called Y2. This is Y3. Next will come Y4. And what these numbers are their binary divisions of the raster. XY is what we call them. It's from Cartesian coordinates. X is on the horizontal, Y is on the vertical. And what it does is divides the raster up into X and Y's. And we could have various divisions. Finer divisions of the higher X's. Now this is the first X that you can see. This is X2, X3. These red bars.
X3 is not yet. It's X2.
No, this is
Wow.
X4. This is X4.
Oh, X4.
There's one missing there which we don't show.
Okay, it goes 4, 8, and 16. It doesn't
And-
go 3, 4, 5, 6, right?
What it's doing is dividing by 2, then it divides by 4, then it divides by 8, then it divides by 16, then it divides by 32, then it divides by 64, then it divides by 128, then it divides by 256, then it divides by 512. And that's our division of the screen. We divide the X and Y's into 1 to 512. My voice was computerized there, what you heard, the voice going up. Okay, and what the program is now doing, it's running through the red, green, and blue bars. This is Y2, what we call it, division by 2 of the screen, division by 4 of the screen, the black and white bars. This is the basis for our other units to use. We can use this as an input signal, or we can use this as a position specifier on the screen. First, we'll look at the red. Now, we're talking about the XYs now. Now, we use, as a test pattern, we have the X's on one input to, we're showing you the X's as a grayscale. So now we're going to do that on the red, 171, 100. And we're going to put a 1420 in this. We want that. Oh, it's not bad. Okay, now what we're going to show you now is that 71040. I will show you this thing which we call a grayscale along the Y's now. 71040. And we can also show you this along the X's, which we'll do momentarily. Right there, and this is our grayscale along the X's. 71052. And showing that we do have hidden tricks up our sleeve. 050. We're going to first center the screen. Showing you that we have hidden tricks up our sleeve. What we're going to do is we're going to shift the reference. Now, for instance, let's say I gave you this pattern here. Okay, let's say I gave you this pattern here. We can shift them. And as you notice, it's now shifting only along the X. Notice that's the Y. We can also shift the Y reference. Okay. If we want, we can now turn on other colors and show you combined X and Y's. Or we can show you combined X and Y's. Since I love red, I seem to do everything in red. I just love red. I'll put in a combination of X and Y's and show you we can shift them both. Then we'll show it to you in color. You notice we can shift both X and Y's. And what we'll now show you is we'll show you putting more colors in, making it somewhat colorful. Hopefully we can we'll show you first on this one. On the red, we'll give you this, as I said, on the red, we'll give you, come on.
Patient.
Be patient. Okay, we'll give you the Y's on the red. We'll bring the greens into the picture. And here comes the green into the picture. There's the green. And we're putting in the green, the Y, the X image, the grayscale on the X. And we'll put into the garble. We're going to put into this magic number, which is the combination of X and Y, which I just showed you before, which should be 63757, as all of you wake up in the audience. There, 1110. Where's the audience?
You're banging the keyboard very hard.
I think it's a teletype. Now what we're going to show you is shifting the XY reference with colors.
What did you add in that?
I added in the blue. And that was the blue part. I can even show you individual components. Cut out the red. Cut out the green. That's what the blue is. You can even cut out the blue if you like. We can divide by 2, doubling the screen in both directions, resulting in 4 of the same. We can get back to where we were, multiply by 2. And we can also use the shift as a correction factor. If you notice the screen is slightly off, we can correct for this slight offness, get it back to our standard screen again. We can go 170.
Okay, so what you are doing, you are scaling, in fact.
This would be a scale factor.
Scale factor, yeah.
And if we scale it down very small, we actually duplicate sections of the screen.
Yeah, so now by combination of scaling and centering the screen by shifting, you can in fact induce a zoom.
A zoom. Now, do we have any demonstrations of the zoom?
No, we don't.
But we're... And, this is quite cumbersome. Okay, that's a foot. Okay. Acrobatics. This chart over here has different numbers. Now, ALU unit happens to be a standard ALU unit, arithmetic logic unit, so digital IC. And if you look over here, we have a chart. We program type of function by a binary number. This low-high represents zeros and ones, or numbers. Next to it, we have the functions. So suppose, let's say, we now want to look at, before I was looking at A, and I had to manually stick in this number here. And before I was looking at B, and I stuck in this number. You notice there's a bar over some of these. Bar indicates negation. I'm not going to go into negation of negation of negation. But now we're going to look at something called AND. And AND would be sitting over here, let's say. And what I would do is I'd put in the number, this would be 1011. Or, turning it into octal. What's octal? It's base 8. What would be the number 13? I'll put in something like that number. I'm not going to put in that number. I'm lying slightly. And we're going to actually, because for some reason we negate somewhere in the system, we're going to put in the inversion called, who knows, number 4. So I'm going to place this in and show you the AND operation. Here it goes. And if you want to sit down with your pocket calculator and calculate every single instance on the screen of zeros and ones, you would find the AND function, which says if both are true, the output is true. If either one is false, the output is false. So in the red, wherever these numbers happen to coincide to be both number 1 on the screen, the best, number 1, you get an on square.
Yes, so what you are saying is an image which is produced by arithmetic or logic, comparing it of two inputs into A and B,
right?
In which you showed first horizontal and then vertical bars.
Yeah.
And this is how they meet. It's a 16 level gray.
16 gray levels, or 4 bits compared with 4 bits.
That's right, I see.
So in this case, you're only going to see, since it's an AND function, probably only 4 bits coinciding, but it still can form a 16-level grayscale.
Right.
But it's ANDing the bits. When both are true, the output is true.
I see.
And it's done on each bit. So you will get 16 gray levels on an output, and that's what the kind of image it gives with one logic operation. We'll give you an example of one of the other basic logic operations called OR. 4 to 1, and here it goes. That's what the OR looks like. It's somewhat similar to AND, but it's slightly different. I'll go back and forth. This is AND again. That's AND. That's slightly different. And this is OR. And that should be exclusive OR. And it looks slightly different from both AND and OR. And these are the basic things. Mixed with a negation, the negation function, you get Boolean operations. And that's the basis of most computer systems, or binary addition, binary subtraction. Now we're going to go to the actual arithmetic part, the plus, minus, and such. Okay?
Yeah, sure. Why don't you make a leap forward?
Okay, let's jump forward. And we're going to look now at A plus B. Now, interesting thing is, since these are x, y's, we get a stair step. So we're going to show you the staircase, or maybe we shouldn't give it away. Okay, now we'll try addition. What do we have here? Look at that. It's a staircase. Well.
Okay.
And this is caused by addition of adding the vertical and horizontal. And it causes a staircase. We can show you the minus, which will be, and let's see what minus would do. This is the minus function. Look at that. The staircase reverses. So that's one of the arithmetic type functions. Now it doesn't look like the logic function. It's pretty much different. Now the more interesting part is saying, what happens if we mix the logic and arithmetic functions? Now, as an example, we're going to do something called A or B plus 1. Okay, we're going to now show you that. This is I like these kind of things right here. and we get a pattern like this. Now you can see in the background the OR function, which I'll switch back to right now. The OR is sitting like this. That's not the OR that we want. Well, it's similar to that. That's, yeah, let's get this back into... Yeah, this is the OR alone. Is that the OR? Come on, Jeffrey. Okay. And this is the OR plus 1. As you notice, the slight change there. That's the OR. That's the OR plus 1. And it adds in all those extra squares. And now I should be giving you... Okay, this is exclusive or overlapped over it. Now it's adding the outputs here, really. Each one is having its own function, but red, green, and blue at the end is added all together. So you add the red to the green to the blue, and you encode it into video signal. And now we're going to add some blue. You want me to change the pattern? You don't like it? Okay, we can do again. We can again shift the reference again. I see the ALU will still, in time, still keep the same function, but now the reference, the XYs which are generating this, are shifted. We can also have programs that change these patterns in time. Let's give you an example of it. We have a program called Walter Wright 2, which is called Maiden Voyage. It's another name for it. And we can show you this is going to change the XYs. Now we're going to leave these same patterns, but by changing the XY patterns, the XY inputs, those A and B things on each red, green, and blue. Okay, so this is the program changing those XYs and giving you this kind of pattern. I think we should zoom it out a bit.
If you could stretch it maybe horizontally, that means make...
Leave the vertical? You like the vertical?
Like a division, yeah, Y division a little bit greater, but not much, just touch.
We should make this 0, I guess. I'll 0 that. 0, 5, 2. Really? You want it both ways? I'll make it both ways. It's going to change finally.
Let you run it for a while so we can see.
Make it larger.
So what
Okay, that's
happened
good.
now? Stretch it.
I didn't stretch it. I'll stretch it.
But don't stretch it too much because it's
I'll stretch it only a little. Okay?
Nice when it's smaller, so we could see
How
the
about that?
texture. That's good.
That's good?
Okay.
Now what we're doing is changing the XYs. We're running patterns through the XY, just running through them, and using those patterns, which I'll mention again, which were A plus B on one set of XYs, there's a thing called
so your
A or B and A or B plus 1.
I see. So your raw material, so to speak,
The
are the
inputs
horizontal and vertical division of the screens, which are kind of accidental because they are running the kind
They're
of...
not accidental, they're programmed, and the program will repeat,
I see.
but the program is meant to just run through these values and
I
it's
see.
not...
They're not aesthetically, I would say, controlled.
Show you the memory. We have a program here, which was done as a promotional tape for, I don't know, I would say a video committee, and so it demonstrates the memory. It demonstrates a use of the memory. It doesn't demonstrate necessarily the 64 squares, but maybe I can even just show you some of these 64 squares. Sitting at the keyboard here, and I'll turn this on, and spelling out something. This is all in the program control, changing the 64 elements of this memory. This is slightly different from these XYs, where the XYs were timed to this X and Y, but we really cannot select a pattern. We cannot set any part of the screen to on or off. It was a changing pattern, a constant changing pattern, which looks stable on the screen like a bar. But we didn't have the control to set a square on section of the screen. And now we can specify 64 different squares on the screen. We can turn it to a different color. Let's say the left-hand side of the screen. We can I'm going to turn the far left-hand side of the screen, top left-hand side of the screen. I'll turn it, I don't know, white over there. You notice that's a square, one of the squares. You can turn it black. I'll turn the one next to it black. And I'm beginning to show the square structure of it, that there are really 8 by 8 squares. We can also do the shift operation on this. Shifting the reference that generates these 64 squares. Now you notice it's going up again. And it's shifting the reference that generates these 64 squares, 8 by 8 squares.
But it indeed is an image that is made totally from a different material in a way that what we saw before.
In this case,
it takes the
stored,
reference
right,
from it, but in fact the organization of this image is based on totally different principles.
Now this is memory in this case,
That's
and memory is now storing this image, but the XYs are used to position where the square starts and ends. We're going to have this program called Maiden Voyage again. We're going to run that again. And now we're going to see that we can change the XY reference. Now, before, this was a set image on the screen, and now by changing the method of addressing it, it becomes more of a pattern, which we'll try to do now. And I'll just switch it to an external input, and what do we give it? 2.6 might sound good. And now, just as a start, you see it has this pattern formed. And now what we'll do is we'll run this Maiden Voyage program.
So what is this pattern? That's the same pattern we saw?
Now this is the same internal stored program.
Mm-hmm.
I can switch back to it for you, 171170. It's the same as this pattern here, which each memory of the 8 by 8 memory elements are still storing the same information, but now we're addressing it differently. So now on the left side of the screen, let's say, we're not just reading out. Actually, these are actually numbered also, which is also interesting. Memory is a form of addressing, that it's referenced by numbers. That this side of the screen right here is number 0. This could be number 1, number 2, number 3, number 4, number 5, number 6, number 7. This could be number 8 in decimal, number 9, number 10, number 11, number 12. We can also number the screen. Now we can have a numbering of the screen in squares. And we can also use these squares to be a control instead of being an image itself. There's a great flexibility between using signals as inputs, using them as controls, or using them as outputs. And they could be inputs to other devices. They could be their own output. In this case, it's an output. Or it could be a control, putting something in when it's yellow. Instead of it being yellow, it would turn something on in here. So it becomes also a control device.
This is an identical principle that other synthesizers like analog systems use. Sometimes they use signals to control.
And 2.6. And now. Okay. So this is what the effect is of scrambling those addresses around. It's the same information stored in the memory, but the memory is being read out differently referenced to the screen. The screen reference is no longer 8 squares by 8 squares. It now is scrambling where they occur, and this is the type of pattern that occurs. Different patterns and different form of addressing with different images. The question of control, how much you control it, what control of the signals, and this is what we're getting as an output. Now, the analytic judgment of this is it can be done. Every signal is specified at every point in time, and if looked at, you can find what they are. But the time to calculate it is sometimes not as quick as just doing it. So.
You mean the accidentality here is the richness of the program, or?
The major part is that it's a program. The program is changing. It's a control source. It's changing the signals, the way the signals occur, sometimes even changing what the signals are. And this is what it looks like when we have memory input. Now, this is another thing which we didn't mention before, that you can mix these a pattern with an XY pattern. And this is two different separate inputs.
It's too complicated. Could you simplify it?
This always goes through like that. Splice it out. So, we turn off the green. Yeah, there's too many things to do. Just the red now.
So there comes an apparent motion of the letters jumping up and down.
Letter, looks like a letter H. This is using the AND function, and it's ANDing something with something. And let me
Funny
stop
that-
it again.
That art square has this half transparency.
Yeah. I'm gonna just deal with the red for a few seconds. I'm gonna switch this to this is not exclusive one. I'm gonna switch to exclusive one. Maybe it will show something kind of just with the red.
That's neat, as they say.
Only vertical. Okay, so I'll go to another function now. I'll put it horizontal now. 171040. I'll put it to the horizontal drift. Going this way. In the horizontal direction. Only. It's the plus function. I'm now going to go to the minus function, which should be very similar to this, I hope. 171100. And for the minus function, it'll be 1446. Yeah, it should be similar. And maybe we'll turn on the green just to show what the reference is doing. 104. Just turn it on.
Yeah.
432. You can't see the
Yeah,
red
it makes
too well.
the background totally solid. Divided.
Turns on the mixes of colors.
But it just is overlap. It's just on all the. Yeah, it does overlap.
Now, have you demonstrated all, or is it something that?
Well, no, I wanted to go through these functions at least just to show what.
Yeah, keep on doing the functions.
I think it is late in the night. It is 3 o'clock in the night, and I don't think we have gotten any colors.
Yeah,
We have run out of everything. We
Yeah.
have run out of new tricks. Yes, we're desperately trying to figure out new tricks, but all the new tricks are just the old tricks.
Same
Let me
old
show
thing.
the same old tricks.
It's good.
The
It's the,
B.
it's the old in and out and in and out.
Oh. And T is there. So why don't you turn it off here?
You should have caught my last image, which it was me yawning.
Can you
Jeffrey.
repeat, sir?
No, it's
So why
unrepeatable.
don't you take this camera?
Oh, I have to give your report. Steina, where are you, please? You are a person, or even you are in fact in color, and usually. Aha.
What's the color of my trousers?
Aha.
Pretty good, huh?
Let me scan you here. This is not that.
Mm-hmm.
Green.
This is like arithmetic
Did you
logic,
look at the
isn't it?
digital?
Could you analyze this image, Jeffrey?
I think it's a combination of vertical and horizontal ankles.
Ankles and angles. Okay, dear friends.
Romans and
I
countrymen.
think this camera is decently sharp, isn't it?
Quite sharp, yeah. This is also arithmetic. Now, to take it slightly out of focus. Slightly out of focus. See, it's like, no, not so much. Just show it as like bits. Like on and off. Ah, there it is. There you are. No, get digital image. Sort of. By the way, show my face. The cameraman in this tape was Steina Vasulka.
Great kid.
Kill it.
So, we've made it.
Report. Steina, where are you, please? You are a person, or even you are in fact in color, and usually. Aha.
What's the color of my trousers?
Aha.
pretty good, huh?
Let me scan you here. This is not bad. Green.
This is like arithmetic.
Did you look at the digital?
Could you analyze this image, Jeffrey?
I think it's a combination of vertical and horizontal ankles.
Ankles and angles. Okay, dear friends.
Romans and
I
countrymen.
think this camera is decently sharp, isn't it?
Quite sharp, yeah. This is also arithmetic. No, so take it slightly out of focus. Slightly out of focus. See, it's like, no, not so much. Just show it just like bits. Like on and off. Ah, there it is. There you are. No, get the digital image, sort of. By the way, show my face. The cameraman in this tape was Steina Vasulka.
Great kid.
Kill it.
So, we've made it.